The challenge of overriding our gene network. In the last episode, we uncovered the core problem behind gene control. Our gene networks weren't built for easy adjustments. They're dense, interconnected, and incredibly robust, designed to lock in their behavior and resist change. But if we want to reprogram these networks for longevity, we'll need more than simple edits. We'll have to override that original design and build a new layer of logic controllers on top of it, a second operating system that ultimately remodels the old one. And here's what makes the challenge even harder. This new control layer has to be built uniquely for each person. There isn't one solution we can copy and paste. So the question becomes, how can we build a personalized control system on top of a network this complex, and do it safely, at scale? What is a microtest? So how do we rewire a network this complex without putting anyone in danger? We start with the smallest adjustment possible, a microtest. A microtest is a temporary tiny nudge to a single gene controller applied in just a small number of cells. Maybe we upregulate or downregulate one gene by only 0.1% from its baseline activity. That tiny adjustment creates an equally tiny ripple downstream, a slight shift in the molecules those cells release as waste or byproducts. And that ripple is what our sensors detect. When millions of people run these microtests in parallel, each of those tiny downstream changes becomes a small data point in the map of how our gene networks actually behave. The key is resolution. The more precisely we can measure those downstream signals, the more clearly we can see how to rebuild the network. What does a microtest measure? What is the signal we're trying to capture? When we nudge a single gene controller, the affected cells release slightly different patterns of molecules into the breath, urine, or feces. These changes are tiny and difficult to measure, but next-generation molecular sensors will detect them with high precision. The result of a microtest is a series of these measurements taken over the next few days. Each timestamp gives us a histogram, a list of numerical values showing the levels of hundreds of thousands of volatile molecules at that moment. But for our purposes, we're only interested in the changes caused by the microtest. To see what shifted, we compare each histogram to your baseline, the normal pattern your body produces when no testing is taking place. Most values rise and fall within their usual range, but a microtest creates a few small deviations from those baseline curves. Those deviations become the data points we use to start mapping the network. How can microtesting help us? If the goal is to rebuild our gene networks for longevity, the results of these microtests help us find the boundary conditions, the places where the system breaks its normal behavior. Real gene networks have loops, convergences, bottlenecks, and hidden gates that can behave in unpredictable ways. So when we nudge a single controller, most values drift normally within their usual range, but some don't. Every so often, a signal collapses or spikes and stays there, pushed outside the limits the natural control system can handle. These extreme shifts matter. They mark the places where the network hits a threshold it can't stabilize on its own. And those are the points where we'll eventually need synthetic logic circuits, tools that can redistribute resources, assist other pathways, or reroute the load. These circuits will help keep the system stable as we move it toward a new normal, optimized for longevity. Sensors turn microtesting into data. Microtesting only works if we can see the results, and next-generation molecular sensors are the missing link. Precision sensors can already be built that detect the tiniest shifts in the molecules we release through breath, urine, or feces. Some will be handheld and used for just a few seconds every 15 minutes, while others will work passively in the background, sampling volatile molecules with no effort on our part. They're based on low-cost microchip technology, designed to be mass-produced so millions of people can use them at the same time. And if you want a deeper look at how this sensing system works, I have a separate video devoted entirely to that topic. The link is below. Microtesting as an information system. If we want to redesign our gene networks for longevity, we're not repairing the old system. We're building a new one on top of it. And even though this whole process looks biological, it's really an information systems problem. In Darwin's Machines 2024, I show how to break complex problems into tiny information packets, and how those packets can be assembled into higher level structures using the same principles we see in natural systems. Useful information emerges from these higher layers, even when the raw signals look like noise. Microtesting is the breaking it down step of that method. And in the next episode, we'll see how those higher level information structures can guide the choice of logical operators, the smart molecules, and how we can automate the assembly of those molecules into chains that form the synthetic logic circuits of the new gene control layer.